Welcome back friends for another lecture on quantum field theory and quantum entanglement. So we were discussing about Dirac spinors essentially, yeah. So the last time we looked at some properties of the Dirac spinor, the discrete symmetries associated with them, and we also looked at the definition of Marana spinors, the Marana spinors from the discrete symmetries itself. One, we introduced the parity and how under parity the u plus and u minus go into minus plus. So under parity left and right movers change one to another, and then there is the other symmetry which is the charge conjugation symmetry. Imposing that condition, essentially what happens is the particle and antiparticle become the same, essentially imposing that condition. What happens is the particle and antiparticle solutions are the same, and so that leads to a reduction of the degrees of freedom, okay, and the reduction of degrees of freedom which gives you the Marana spinors, which are all completely real spinors, and the corresponding gamma matrices are completely imaginary. Because they are imaginary, the Lorentz transformations associated with them are completely real, and so the Dirac equation itself is real, and it leads to real solutions of the Dirac equation. Okay, good. Now let us continue further. Essentially let us start with looking at simple plane wave solutions of the Dirac equation. Okay. Solutions of the Dirac equation. So I am expecting that most of you know these solutions, so I will be a bit fast, but anyway, let us assume I am doing it only for completeness essentially. So the Dirac equation is given by gamma mu del mu minus m psi is equal to 0. One of the solutions we can immediately write. Let us just assume psi is equal to u of p in momentum space e power minus I p dot x essentially. Okay. So this is the plane wave part, and this is the spinorial part. Okay. Now let us put it back into the equation essentially. Okay, let us put it back into the equation. So I have I gamma mu. So putting it back into the equation. Say, let's say, okay. So in the equation, say this is 1, so in equation 1 we have I del is nothing but p mu, so gamma mu p mu minus m psi e power this thing, okay, gamma mu p mu minus m u bar of p, u of p is equal to minus m p mu sigma mu, okay, p mu sigma bar mu minus m u of p bar is equal to 0. Now sigma and sigma bar I introduced in the previous class. They are saying that sigma mu is equal to 1 sigma I, sigma bar mu is equal to 1 minus sigma I. Okay. So this was introduced to this essentially in the earlier class, and this is the 4×4 form of the Dirac equation written in terms of two component, meaning each of this thing is essentially, here there is a 1 2×2, here also there is a 1 2×2 part essentially. It is written in terms of a block diagonal form of 2×2 matrices essentially. Okay. Okay, very good. Okay, now with this, let me write u of p has a form root of p dot sigma, this can be seen as into xi we will define what this is. Root of P dot okay, let us put P, let us not put this thing, P dot sigma bar, because we have distinguishing sigma and sigma bar into xi. We will see how this work out essentially, and we will say that xi dagger will be a normalization factor. Okay. So, with this then how do you any two component you can have a normalization. So, with this now let us fix what is it. So, u of p this is the solution of the u of p essentially. So, the spinor will have these two components essentially xi and a 2 by 2 component in this particular fashion. Now, similarly we can ask the question, what happens if you have a negative frequency. Now, sigma bar is this one, sigma bar mu is equal to this one essentially. Now let us say P dot sigma u2 is equal to m u1 and then P bar sigma bar u1 is equal to m u2, assuming u is equal to u1 u2. Let us say that u has two components essentially u1 and u2. So, then from this you can get that P dot sigma u2 is equal to m u1 from the equation essentially from the equation. So, you put it back into the equation essentially, and then you have got P dot sigma bar u1 is equal to m u2. Okay. With this you can get the desired form, you can work it out essentially, you can take out the thing, and because you have P dot sigma bar and times P dot pitma using the following the identity, you using the identity P dot sigma, apply the same thing again, and P dot sigma bar is equal to P0 square minus Pi Pj sigma I sigma j is equal to P mu and that is equal to m square essentially. Okay. So, this is that this relation essentially will give me that you get the promised result essentially, that this is the form which is correct essentially. Using this you will see that you will end up having the solutions that u1 is equal to P dot sigma root of P dot sigma bar sum xi is equal to m root of P dot sigma dot xi. I am not okay. So, this gives me the form of the u1, and similarly you can work it out that u2 okay will give me the other part essentially, the u2 will give me this part essentially, this P dot sigma bar. Okay, u2 will be P dot sigma bar. So, you can just work it out essentially that if you assume that you have P dot sigma times xi and P dot sigma bar times xi, you end up having these solutions. Okay. This is for the positive energy solutions, this is for the positive energy solutions because I assumed positive energy. You can also do the same thing for negative energy solutions also. Okay. Now, I did not do a detail, but this details can be worked out, detailed calculations, and this is the form you will end up having, that this is the form for the positive energy solutions. There are two of them essentially which will give me this particular thing. Now for negative energy solutions we follow the same thing. Okay, you have psi is equal to V of p e power I p of x. Okay. So, the Dirac equation in this case just becomes E gamma mu p mu plus m V of p. This is equal to m, this p bar actually, okay, p mu sigma mu and p mu sigma bar mu m, all acting on V of p bar is equal to 0. Again you end up having the solutions to be V of p bar is equal to root of p dot sigma some eta and root of minus p dot sigma eta, where eta dagger eta is equal to 1. So, this is a 2 component spinor which is like 1 0 0 1 so on. So, this is also the same thing. So, xi is a okay, I should put it here, it is a normalization. So, 2 component spinor which you can take it to be 1 0 0 1 and so on, so essentially. So, okay. So, 0 1. So, that see if you take 1 0 0 1 it works out essentially, okay, this works out very well essentially. So, you can have xi is a 2 component spinor, you can have first component xi 1, xi 2 would be 0 1, say for example. We will see this in a second essentially. Okay. So, you have, so assuming the 2 component spinors essentially, the spin the solution would be so you can write down all these solutions. So, let me write down okay, say for example same thing, eta is equal to 1 0 and eta 2 is equal to 2 0 1. So, you will have 2 solutions of u1 and u2. Okay. So, consider one particular solution, you can think of static solutions and so on. So, okay, let me give a homework problem for so p bar is equal to 0 static essentially, okay, it does not move essentially, and xi defines the spin of the particle, okay. In this case essentially, okay, show the Dirac spinor has the form u of p, the particles essentially is equal to root of e minus p 3. So, let us just fix okay some momenta essentially. So, what is okay, let me not write the solution, give me the form of the form in this case and to boost it in a direction of z, okay, in z direction. So, you have P mu is equal to E 0 0 P 3 or P z essentially. So, give the form in this direction essentially. So, what has the form of this thing essentially. So, for the okay. So, you will show that, okay, you can see that after all this you will end up having say something like u of p would be, we can see that E minus P z 1 0 root of E plus P z 1 0 okay. So, this is the another one of the solutions, and then the other solution would be the u solution, u1 solution is this, the other solution is 0 1 0 1 okay. So, you can have for this is the xi 1 is equal to 1 0. Similarly, solution would be xi 2 would be 0 1 solution. So, that solution would be, so for example, would be u of p is equal to root of E plus P z 0 1 E root of E minus P z again 0 1 okay. So, this way you can write down the plane wave solutions of the Dirac equation, and similarly you can write similar expressions for similar expressions for negative energy solutions. Now, I know that I am rushing fast because I am not going to the details of this writing down explicitly all the details of the plane wave solutions, but what is more important are the inner products and the outer products of these spinors, which will play a big role in our computations essentially. So, what are the inner products and outer products of this computation of these spinors? So, there will be enough homework problems on this, and I hope you all have done the Dirac equation and solutions earlier, but this will be just a repetition and a recap essentially. Inner product. So, the inner products is essentially you take u of r, okay, which is essentially r is equal to r and s are essentially the solutions xi 1 and xi 2, dagger u of s of p, let me write it in the standard notations, u dagger of r p okay, and then u of dot u of s p r s is equal to 0 1, which are essentially or 1 and 2, essentially 1 and 2, these are the two spinor indices essentially, or the spin indices, is equal to 2 p 0 delta r s essentially. You can prove that essentially, okay, and the Lorentz invariant u bar r p u dot s s p is equal to 2 m delta r s. So, similar thing for the antiparticles also exists, essentially the antiparticle wave functions. So, v bar okay, these are the inner products essentially. So, the inner products v bar v will give me minus 2m delta rs. And you can also show that they are orthonormal to each other. So, you have u bar rp times v bar v of sp is equal to 0, u bar dot v is nothing but 0. Similarly, you can take u dagger and v dagger are also 0, same thing, u v dagger u is equal to 0 and so on. So, similarly. So, they are orthonormal to each other. So, these are sometimes called the orthonormal conditions essentially. Then there are the opposite conditions or the outer products of these spinors essentially. So, these proofs are left for exercise essentially. I would expect all of you to do it. Okay. So, outer products, this also are interesting, these are important essentially. So, this will give me S is equal to 1 to 2 US P U bar S P is equal to P slash plus M. Similarly, for the V, S is equal to 1 to 2 Vs of P V bar S of P is equal to P slash minus M. Okay. Or in the other notation we can put the S in the bracket itself essentially. So, summing over all this thing, this is the outer product. So, this is like a matrix. So, this is a matrix. So, whereas this is a number, this is a number because this, whereas this is a number, it is 0 or m, or if you normalize m, it just becomes 1 essentially. So, whereas this is a it is a matrix essentially, these are matrix equation. Now, remember in the massless case what happens essentially, tell me u bar is an independent thing and v bar is an independent thing essentially, they do not get related essentially, only with the mass term they do get related with each other. Okay, good. Now, so let me just finally, before going into the quantization, let me just look at some conserved currents essentially, let me just do, we have already seen two conserved currents which are essentially the parity, these are not currents, these are discrete symmetries. We have seen the parity and charge conjugation which are discrete symmetries. Let us look at some other symmetries. And after this we will move to the quantization of the Dirac equation, Dirac fields essentially. So, let us look at first thing is space-time translations. Under space-time translations, delta psi goes to epsilon mu del mu psi essentially. So, space-time translations, the generators are p mu, and the Lorentz transformations we have already seen, and this is given by del mu essentially. This is mu mu. So, this gives me something called the energy momentum tensor del mu nu T mu nu I psi bar gamma mu del nu psi minus eta mu nu L. So, the derivation, okay, you have to do it essentially. So, okay. So, under space these are translations under the generator is P mu, this I have mentioned it. So, the momentum, and that is the reason the 4 momentum, that is the reason we have the variation in psi to be given by epsilon mu del mu essentially. So, this gives us under the Noether's theorem and so on, Noether's theorem, okay, conserved quantum current to be the space the energy momentum tensor. Okay. Now, because the energy momentum conservation essentially is okay, this is the energy momentum, so you can use equations of motion on it essentially. So, if you use the equations of motion, okay, so you can use I del slash minus m psi is equal to 0. This means we can set L is equal to 0 in T mu nu, okay. The variation in L is 0 because of the equations of motion. Okay, implies L is equal to 0. The variation in the equation in the limit of the equation of motion, imposing the equation of motion, what is the L gives me what? The Lagrangian essentially psi bar gamma psi bar I del slash minus m is equal to 0. So, you end up having this T mu nu only to be I psi bar gamma mu del mu psi, and in particular the total energy E is equal to integral d cube of x t 0 0, the 0 0 component essentially. So, this gives me is equal to I okay d cube of x I psi bar gamma 0 psi dot. Now, psi dot I can again use the equations of motion, and that gives me d cube of x I psi dagger gamma 0 minus I gamma I del I plus m psi. So, this is the total energy which you can get essentially, which again here using equations of motion. So, the total energy of the system in the Lagrangian you can get it from this particular thing. This is psi bar only the space component minus m of the Lagrangian essentially, which is nothing but the total energy of the system. Now, you can ask the same question, what happens under Lorentz transformations. So, because remember the Poincare transformations are space time translations, and then the second one is Lorentz transformations. This we have already seen a little bit already. So, I will be a bit fast. So, delta psi in this case again would be minus omega mu nu x nu del mu. So, this is just rotations psi alpha plus 1 by 2 omega rho sigma s rho sigma. This is the first term, okay, alpha beta psi beta. So, how did we get this? We have written omega mu nu, okay. this is just a variation in this thing, omega mu nu, the derivative, this is nothing but the rotation part essentially, and then this is the part. So this omega mu nu is half capital rho sigma m rho sigma mu nu, right? This is what it is essentially, and the generators m rho sigma mu nu are given by eta rho mu delta sigma nu minus eta sigma mu nu, okay, delta rho nu. Okay. So what you are seeing is that you applying the Lorentz transformations, you end up looking at the variation in the Dirac field. You have delta psi alpha, the component, is equal to minus omega mu nu x nu del mu psi alpha, which is minus 1 by 2 s mu nu alpha beta psi beta. Okay. This is, so you can write everything in terms of omega mu nu, you can bring it out, because where we can use essentially that omega mu nu is nothing but the capital omega mu nu, okay, capital omega mu nu, okay, which is used in the Lorentz transformation essentially. So this gives, okay, this guys, so this gives you a thing j mu rho sigma, okay, is equal to x rho t mu sigma minus s sigma t mu rho minus psi bar gamma mu s rho sigma psi. This is the conserved current associated with it essentially. Now we, so what we have is essentially, we have, okay, we see that we have an extra piece compared to, okay, so there is an extra piece which is s psi bar gamma mu s sigma rho psi, essentially there is this piece which comes in essentially, okay. This piece, as normally we will see another way, I will mention it in another way in non-relativist reduction a little bit. This piece after quantization of the current essentially after the quantization of the Dirac spin essentially is the internal angular momenta sets the internal angular momenta of the single particle states of the Dirac spinor. So that means after quantization, meaning what I meant to say is after quantization, which we will see, and show that the spin is half. Okay. So this is so what we are trying to do is relate the transformation properties of the Dirac spinor and the conserved currents associated with the Dirac spinor under the transformations essentially, and we are relating it with the representations of the Lorentz group essentially, and saying that what are its internal angular momenta of this one particle state after quantization. The one particle states after the quantization will end up being having spin is equal to half. There is an easier way of doing this, which we have done in the relativistic quantum mechanics course, is by writing down in terms of the Pauli equation essentially, which is nothing but doing the non-relativistic reduction and everything essentially. Okay. Okay. So we will stop here. We will see that okay, there is various ways of looking at the Dirac spinor gives you a spin half particle essentially. Okay, this is just a conserved current under Lorentz transformations, and from there we can see that, or we can just see the Clifford algebra representations. And you have already seen this part essentially in the previous lecture, where we shown that the Dirac spin should be spin half because it transforms under the SU2 as half 0 and 0 half. So the spin half particle of the Dirac spinor would always the spin of the particle, internal momentum of the particle which is transforming in the Lorentz transformations and in the Clifford algebra in the Dirac spinor is spin half anyway, because it transforms as a fundamental under the product of the two SU2s essentially. Okay, that is one way of saying. There is another way of arguing essentially. Okay, and so with this and with this I will stop here, and now we will start looking at quantization of the Dirac field from the next class essentially. Okay, so let me stop here, and thank you very much essentially. Okay.